Hello everyone. Today we'll be looking at a very important paper in the domain of adversarial machine learning, which is titled Explaining and Harnessing Adversarial Examples by Ian Goodfellow and his team. This paper was presented in International Conference on Learning Representations, or ICLR, in 2015. So all the materials from today's presentation have been taken from this paper. So today's presentation is divided into three parts, where in the first part, or the introduction part, we'll be looking at what adversarial examples are and how exactly do they affect machine learning models. Then we'll be looking at the generation of perturbation, or how these adversarial examples are generated. And finally, we'll be looking at the discussion section, where we'll be going through some of the claims or alternative hypotheses that the authors presented. So what exactly are adversarial examples? So the definition says that these adversarial examples are basically inputs formed by applying small but intentionally worst case perturbations to examples from the data set. So as you can see over here, this particular pattern that you see is, in our case, the perturbation, and it is being applied to a data set, which is the image of a panda. And what it does is, so it basically produces a perturbed input, which results in the model outputting an incorrect answer with high confidence. So as you can see, this image over here is our output, perturbed output, and it is being classified as a given with very high confidence of 99.3%, which means that the machine learning model has been fooled. So the reason being, we are claiming that it is being fooled is because the image to a normal human eye is still of that of a panda, whereas it is being classified as a given. So we can say that the machine learning model has been fooled. Now, how exactly do we do this? We basically generate using an algorithm, which we'll be discussing uh, further into the presentation. So we basically first generate this noise that you see over here, which is a perturbation, and then we add it to the image. In our case, it's an image of a panda. In it could be any data set. For example, in case of in a natural language processing task, this could be a sentence where we input specific words into the data set, and then we have a perturbed data set. Now, uh, just to remind you, or to let you know that this perturbation of this process takes place during the testing phase, where we add this image or add this perturbation to the testing images, so that during the testing phase it is misclassified. Out of the various observations that were made throughout this paper, one of the most important one was that when the same adversarial examples were tested on models with different architectures, trained on different subsets of the same training data set, they were still being misclassified in a similar fashion. The effects of this adversarial example were thus universal across different models as long as they had the same characteristics. The reason the authors thought that the adversarial examples had this sort of an effect was that maybe the adversarial examples were taking advantage or exploiting certain blind spots in the training algorithm. For example, when a certain algorithm classifies this image as that of a dog, it maybe looks for certain patterns in the image, such as straight vertical lines of the legs in this part of the image. So whenever the model finds these patterns, it classifies this image as that of a dog. But whenever we have any changes in this part of the image, it is not being reflected in the decision, or it does not contribute to the decision of the model. So what the adversarial examples basically do is they take advantage of this part of the image. So they make changes in certain blind spots so that the models do not learn to classify certain perturbed images from that of the original one. As a result, what happens is these models or these classifiers are not truly understanding the underlying concepts that differentiate certain images, even though they have high accuracy for for the data set. So, what the authors concluded was that naturally occurring datasets work well when they are trained on the model, but whenever we have datasets that are artificially created or datasets that have perturbations that do not occur naturally, the models struggle to differentiate between them, and the accuracy of the model uh, decreases significantly. Also, previous works that were done on this domain claimed that the reason why the models behaved in such a fashion for adversarial examples was maybe because of the extreme nonlinearity of the deep neural networks. Uh, or in other words, if the models were extremely nonlinear or complex, the adversarial examples had a fooling effect on these models. Also, insufficient model averaging and insufficient regularization could be a reason behind these models being unable to classify the images correctly. So, but the authors of this paper, they said that no, it's the linear behavior in the high dimensional spaces that is causing the models to be fooled. If a model has a linear behavior, it is highly likely that the adversarial examples will be able to fool it. Also, the algorithms, the authors found that generic regularization strategies that were used to regularize the models, such as dropout, pre-training, and model averaging, does not have any effect on the model's vulnerability, or it does not improve the reliability of the model when they are tested on adversarial examples. Instead, the authors found that nonlinear model families such as radial basis function networks were naturally resistant to adversarial examples. One reason could be because radial basis functions gave a low confidence result when they were tested on outliers, and since adversarial examples are an outlier, the radial basis functions gave a low confidence result and were naturally immune to these adversarial examples. In the next section, we'll be looking at the method that the authors proposed to generate perturbation and how it was incorporated into the original image to form the adversarial examples. Also, we'll be looking at how these adversarial examples and why these adversarial examples have an effect on the models. So now we'll be looking at why the authors claimed that the linear nature of the models was what was attributing to the adversarial examples behaving in such a way when they were tested on these models. So suppose we have an adversarial input x tilde, which is given by the summation of the original input x and the perturbation nu. So when the perturbation is added to the original input, we have a perturbed or the adversarial input. Now, how do we generate the perturbation? We basically do it in such a way that the maximum absolute value amongst all the values in the perturbation is smaller than a certain threshold epsilon, such that the sensors and the data storage can discard them. So in other words, we can also say that the L infinity norm of the should be smaller than a certain threshold. If that is the case, we can expect that the classifier F, uh, we can expect that if we have a classifier F, we will have the same output for the original input and the perturbed input. So uh, so so now that that is out of the way, uh, how do we find the output? The output is given. So for example, if we say that y in our case is the output, it is given by a simple linear model. So if we consider a simple linear model over here, the basic perceptron, we can see that It is given by the summation of the input multiplied by its weight. So the weights in our case will be given in a vector given which is represented by omega. This is our weight vector, and if we multiply it with our input part of input, which is x tilde, we will have our output y. Now, if we replace the equation of x tilde with the one that we saw originally, we will have this equation that you see over here, where the weight vector is multiplied with the original input as well as the perturbation. In this case, the activation of this model is given by the matrix multiplication of the weight vector transposed with its with the perturbation. So, as I've just said, the perturbation, which is given by omega transpose multiplied by the perturbation, causes the activation to linearly grow by epsilon mn, where the epsilon is a threshold that we have just mentioned in the previous slide, n is the dimension of the weight vector, and m is the average of the values in the weight vector itself. So we can see that the perturbation grows by a linear in a linear fashion. So for high dimensional problems that have many input values, we can see that we can make many infinite changes to the input, and what it does is it basically these small changes in the input add up to be a large change in the output. So what basically is happening is that if we have an input that is of a very high dimension, each of these dimensions will have an effect on the output, and all the effects added together will have a very large output, such that the it might change the output of the classification altogether. So we can conclude, or the authors concluded, that the simple linear model can have adversarial examples if its input has sufficiently large dimension. So this is how the authors claimed that the linearness of the models is what is attributing or what is contributing to the adversarial examples behaving in the way they are doing. So far we have been looking at how adversarial examples affect simple linear models, and how small changes in the input affect or create large changes in the output, such that the decision of the model is modified or changed. The So now we want to look at how nonlinear models are being affected by these adversaries. So for that, we take, for example, nonlinear neural networks such as LSTMs, ReLUs, and Maxwell networks, which are all designed to behave in a highly linear fashion. So this linear fashion is maintained so that they're easy to optimize. Now, because they have this linearity in them, there is always a cheap and easy way to generate perturbations for this linear model, such that the neural networks itself are full. One such approach that the authors proposed in this paper is named fast real insight method, which is highly popular and the basis for a lot of other advanced algorithms for generating perturbations. Um, the equation for this perturbation is given here, and if you look closely, we can see that given the parameters of the neural network theta, the input x and the output y, the cost of the function of training a neural network is given by j, whose gradient when passed through a sine function gives us the uh, perturbation itself. The strength of the perturbation is moderated by the epsilon, by the threshold epsilon. The higher the threshold, the larger the perturbation. The name fast reading sine method comes from the sine function that is used in the equation, and the gradient on which the sine function is run. So when the adversaries are generated using this method and run on in this dataset, we can see that for a shallow softmax network, almost 100% or all the images, all the adversaries are misclassified with an average confidence of 80% almost. Whereas for a maxed out network, we can see that 89.4% of the images are misclassified with an average confidence of 97.6%, which is very high. So this shows that the models are very confident in misclassifying these images, and almost all the images are misclassified. These high error rates now prove or support that the fact that the adversarial examples are linked to the model linearity. So if the models are linear, the adversarial examples are more likely to affect it. So let's take as an example a simple case of a logistic regression, so that we can see how the FGSM affects it. The equation of the simple logistic sigma function is given here. So if we go back a few slides, we can see that the perturbation is given by this equation, which now we'll try to replace in the equation given here. To do so, I have shown the derivation over here very briefly. We can see that the perturbation x tilde can be broken down into the original input x and the perturbation nu multiplied with the transpose of the wet vector. Now, it is given that using the FGSM method, the perturbation is given by the sine function of the weight vector omega multiplied by the or regulated by the threshold epsilon. So when we replace this equation of nu or perturbation in the original equation, we can see that after a slight rearrangement, this is what we have, and it is also given that the transpose of omega when multiplied with the sine function of omega itself can be rewritten as the L1 norm of omega. So what we have over here is now the equation for the perturbed input, and when we replace it in the original equation, this is what we have, which is the adversarial version of logistic regression that we have to minimize. So this image here shows us a visual representation of the logistic regression model that we have just seen, and how it affects the accuracy when trained on in-list dataset. The first image here is the weight of the logistic regression model when trained on in-list data, and the second image is the sine function applied on the weight of the one that we see in the first image. Uh, the image C here is the data set that is used for the discrimination task of the task of discriminating between 3s and 7s. The accuracy for this, or the error rate for this task using this data set was approximately 1.6%. But when we use the estimate on this data set, the error rate jumps to 99%, and the perturbed inputs are shown over here. Even though it is clearly, understandable to the human eye that the images are of 3 and 7, the model has no idea what these images are of, and it completely misclassifies the discrimination task. One of the co-authors of this paper went on to run some further experiments to see how training on a mixture of adversarial and clean examples affected the neural network, and whether the neural network could be regularized somewhat. It was seen that the neural network was regularized to some extent. For the data augmentation part for this experiment, the training inputs were used which were less likely to occur naturally. One effective regularization used for this approach is given by this equation, where you can see that the first part of this equation is the cost function for the clean inputs, whereas the second part here is the cost function for the perturbed inputs, and they are both taken into consideration for this regularizer, but in a ratio given by alpha. When this regularizer was used in the experiment, it was seen that after training, that before training, the error rates were 0.94%, which reduced to 0.94% after training. But a more important observation was that the models became somewhat resistant to adversarial examples. The error rates dropped from almost 90% to as low as 17.9% after the training, which was a drastic change in the error rates, even though the average confidence of the misclassified examples was still high, or of about 81.4%. So the authors attributed this drop in the accuracy to the universal approximation theorem, saying that it was because of this reason that the deep neural networks were more resistant to the adversarial perturbations. Um, so now finally, the last section we'll be looking at some of the further experiments that the authors run and what observations they made from those experiments. One such experiment was to see the effect of model capacity and how the effectiveness of adversarial examples were affected by it. So it was seen that models with low capacity were generally less confident with their predictions. One example could be the shallow RBF network that we mentioned previously. We have said that it can only confidently predict the positive class in the vicinity of mu, since it's a nonlinear network. Elsewhere, which means that outside the vicinity of mu, the default answer of prediction would be that the class is absent, or that or even if they did find the class, the confidence would be very low. So this makes RBF networks naturally immune to the effects of adversarial examples. So uh, the uh, uh, we could say that RBF network was one way we could tackle the problem of adversarial examples. Uh, an example experiment run by the authors uh, on the MNIST dataset showed that when an RBF network with no hidden layers was used, an error rate of 55.4% was given using the adversarial examples generated by FGSM. However, the confidence of these examples, or the confidence of the answer, was only 1.2%, which is almost negligible. So the network was classifying the images as a different class as opposed to the original correct answer, but the confidence was very low. So we could disregard the answers completely. Uh, but on the other hand, the average confidence on the clean test example was decent, which was almost 60.6%. Now, one could say that because RBF networks are naturally immune to adversarial examples, could we use them in other networks as well so that the adversarial examples have an effect on them? The answer would be no, because RBF units are unfortunately not invariant to any significant transformations, so they cannot generalize very well across other machine learning models. Uh, So now the question arrives that why do adversarial examples generalize? Uh, as we have mentioned earlier, that the experiments run by the authors showed that machine learning models having different architectures that were trained on different disjoint training sets still misclassified adversarial examples. Uh, but one important detail that we did not mention earlier was that uh, all these adversarial examples were misclassified as the same class. So, for example, if we took the instance of a panda image, like we mentioned earlier, and it was misclassified as given by one of the machine learning models, it would be the same across multiple machine learning models, uh, which is a which is because the adversarial examples are generalized across all the machine learning models. Uh, so why is it generalized? Uh, and what are its effects? So the reason being the reason why it is generalized is because the classification weights that are obtained after training are the same, which makes the adversarial examples also stable. And because the weights are same, the output of of these machine learning models when the adversarial examples are given are also same. Um, Therefore, as you can see over here, it's written that the multiple classifiers give the same class to the same examples. The authors also wanted to test some alternative hypotheses and tried to see whether they were true or not. One such hypothesis is that the generative training could provide additional constraint in the training process, so that the models could clearly distinguish between real data and fake data. Um, so they used an architecture that ensured that the generative model, or the generative part of the model, responded to the adversarial examples only. And it was seen that the error rate was still very high, approximately 19%. Uh, this showed that generative training was not alone sufficient. There would be some other forms of generative training that could be um, more resistive to the effects of adversarial examples, but uh, just being generative is not alone sufficient. So another hypothesis was that so individual models might not be as effective in combating adversarial examples, but the averaging of multiple models can somewhat uh, dampen the effects of adversarial examples. Uh, to this hypothesis, after some experiments, the authors did find that ensampling to some extent helps limiting the effects of adversarial perturbation, but it is not completely removed. It is only limited. So this shows that ensampling is not still a good solution to combat the effects of adversarial perturbation.